Hi, I'm Miss Mixell, and I'm one of the material science engineering teachers at Eagle Crest High School. Today's play posit is going to look at glass, an amorphous material. And as we review the glass bead on a wire lab, we're going to look at what a hydrate is, how we calculate the molar mass, and how we find the percent composition of a hydrate. So in the glass bead on a wire lab, we started out with a solid white powder, an opaque powder, borax, something that you would find in your laundry room. And borax is a hydrate, meaning it's a compound with tin water molecules attached as part of its crystal structure. When we heated it up, it became a transparent glass. And depending on which metal we used, the nichrome wire loop or the copper wire loop, it was either a blue or a green color as the ions were absorbed into the material from the metal wire. And the reason why it became a transparent material is the crystalline structure, the regular orderly arrangement of atoms, changed from crystalline to amorphous as the water molecules were evaporated and removed from the borax. So solid glass is an amorphous material that is transparent in nature. So let's take a second to review some words. Opaque means it doesn't allow light to be transmitted through. Opaque objects cannot be seen through. Whereas transparent allows light to pass right through them. Objects can be seen through transparent materials. And translucent allows light to go partially through, but doesn't allow detailed shapes to pass through, so it's semi-transparent. So just to make sure we understand, here's our three key vocabulary words: transparent, translucent, and opaque. I would love for you to take a second and open a new tab and Google "why is glass transparent?" and watch the following YouTube video that's about 4 minutes long by Mark Medowinick. This is an excellent video. I just can't embed it into the play posit because of copyright issues. But this really walks through the property of transparency, which is fundamental to glasses. And I'll take a second to ask a comprehension question after you watch the video in the play posit. So our big learning target today is how do we find molar mass and percent composition of a hydrate? You definitely want a periodic table in front of you, although I will provide an example of one on the screen. So we're going to be looking at hydrates today. And a hydrate is simply a compound that exists in a hydrated state, meaning there's a specific number of water molecules present for each molecule in the compound as part of the crystalline structure. The hydration number is simply the number of water molecules that's attached to the compound as part of the crystal structure of the hydrate. So we can see magnesium sulfate heptahydrate below. Hepta is the Greek prefix for 7. The hydration number of this would be 7 because it has 7 water molecules attached to a magnesium sulfate as part of its crystal structure. So desiccants are hydrates that absorb moisture from the air. And I'm sure you've seen these in packaging as you get new shoes or other things in the mail. The purpose of a desiccant is to absorb moisture. This allows us to ship things and package things in a way that even if they remain in their package for a while in a high humidity environment, they won't mold or mildew within the package. Just a couple of more vocabulary words as we get going. Hydrate versus anhydrate. So many ionic compounds soak up water and become hydrates. Before absorbing water, they're referred to as anhydrous or without water. After absorbing water into their crystalline structure, they're known as hydrates. Cobalt chloride hexahydrate is an excellent example. It's an old-fashioned weather detector. It was basically used as a humidity detector in people's houses. We can see that the color changes. When it's well hydrated, it's that vivid kind of pink color. And when it's anhydrous, it is the purple color. So it's a way to detect how much moisture is in the air as an old-fashioned humidity device. So again, Anhydrides are compounds without water molecules attached. A compound that is normally a hydrate but's lost its hydration water is said to be anhydrous. So if we look at barium chloride with 2 water molecules attached would be known as barium chloride dihydrate, di being the Greek prefix for 2. Whereas if the water molecules are evaporated and removed, it would just be anhydrous barium chloride. So what happens if you heat up a hydrate? In this example, we can see copper sulfate pentahydrate, a very pretty blue crystal. If I heat it up over a Bunsen burner, we can see that that blue changes into a white substance. And that is because the water molecules are being decomposed or evaporated from the crystal structure. Once all the water is lost, that white powder that's left behind would be referred to as anhydrous copper sulfate without the water molecules. All right, let's take a second and learn how to calculate the molar mass of a hydrate. So molar mass is the mass of 1 mole of any element. It is the average atomic mass in grams, and we can use the periodic table as a reference for it. So if we look at our periodic table, we can see on the key or the symbols in the middle that the average molar mass of a substance is shown right below the atomic symbol. In this case, we're looking at mercury, Hg, and its average molar mass is shown as 200.59. We're going to always round that to a whole number. So for mercury, we would say it has a molar mass of 201 grams per mole. Take a second, please, and find the average molar mass of magnesium, Mg. Hopefully you told me that it was 24. When we round 24.31, we should get 24 grams per mole. All right, what would the molar mass of water be? We're going to use the same process, but we need to note that water has H2O, 2 hydrogens attached to 1 oxygen atom. Thus, we need to find the mass of the hydrogen portion of water as well as the oxygen portion of water and add those values together to get the mass of the whole thing. H2, if we have 2 hydrogen atoms, each with a mass of 1, the hydrogen part would have a mass of 2 grams. Oxygen, we only had 1 atom of in a water molecule, which has a mass of 16. So if we add the 2, the hydrogen part, to the 16, the oxygen part, we get a molar mass for water of 18 grams per mole. All right, take a second and determine the molar mass of SiO2, silicon dioxide, sodium carbonate, Na2CO3, sodium connected to carbon and oxygen, and calcium sulfate, or calcium bonded with sulfur and oxygen. All right, hopefully you told me that the molar mass of silicon dioxide was 60 grams per mole, and that's because we have 1 silicon atom with a mass of 28 and 2 oxygen atoms, each with a mass of 16. So 28 plus 32 would give us the mass of the whole compound, or 60 grams per mole. For sodium carbonate, we should get a molar mass of 106 grams per mole. We have 2 atoms of sodium, each with a mass of 23, 1 atom of carbon with a mass of 12, and 3 atoms of oxygen, each with a mass of 16. When we add up the masses of all of the elements within the compound, we get the mass of the whole compound, or 106 grams per mole. And for our final problem, calcium sulfate, you should have gotten a molar mass of 136 grams per mole. Now let's take it a little bit further and look at how do you find the molar mass of a hydrate? So calcium sulfate times 2 water molecules. In other words, calcium sulfate dihydrate. We're going to do the exact same process, except now we have to account for the molar mass of the 2 water molecules as well. So we're going to add up the mass of the calcium sulfate part, 1 calcium, 1 sulfur, and 4 oxygens. That gives us a mass of 136 grams per mole. We'll also add up the molar mass of the 2 water molecules. We have H2, 2 atoms of hydrogen, mass of 2 grams, O, 1 atom of oxygen, mass of 16 grams. In other words, a water molecule has a mass of 18 grams per mole, but notice we have 2 water molecules present. So we're going to need to take that number and multiply it by 2 before we get the mass of the whole thing. The calcium sulfate part was 136 grams. The 2 water molecules are 36 grams. So all total, we have 172 grams per mole. You try it. Can you find the molar mass of copper sulfate pentahydrate? Hopefully you got a molar mass for copper sulfate of 160 grams per mole. 1 copper atom, 1 sulfur atom, 4 oxygen atoms. Water has a molar mass of 18 grams per mole, but we are going to need to account for the 5 water molecules that are attached. So 18 times 5 is 90, which gives us a molar mass of 250 grams per mole for the entire hydrate, copper sulfate pentahydrate. We're almost done. Now we need to find percent composition. So to find percent composition, we're looking at the percent by mass of each component of the compound, the hydrated and anhydrous version, the water version versus the whole thing. So we're going to take part divided by whole and multiply by 100. So what's the percent composition of water in calcium sulfate dihydrate? If we look at our previous work, we need to identify our part and our whole for this question. It wants to know the percent composition of water, so the water portion of the molecule had a mass of 36 grams, whereas the whole, or the mass of the entire compound, was 172 grams. So if we take the mass of the water portion, 36 grams, divided by the whole, 172 grams, and then multiply it by 100, we can see that we are 21% water in calcium sulfate dihydrate. Thus, if we're 21% water, the anhydrous part of this compound would have a percent composition of 79%, because the 2 should always add up to 100. So we don't have to do the calculation. We always could. We could take 136 divided by the whole of 172 times 100, but we should be able to confirm that it's 79% anhydrous compound and 21% water. Your turn. Can you calculate the molar mass of iron 3 chloride hexahydrate with 6 water molecules attached? You should have gotten a molar mass of 269 grams per mole because we have 1 iron atom and 3 chlorine atoms, making the molar mass of the iron chloride part 161 grams per mole. Water has a molar mass of 18, but there's 6 of them, so the water portion is 108 grams per mole. Altogether, it would be 269 grams per mole. If we want to know the percent composition of the anhydrous compound, we're going to need to divide the anhydrous mass, here's our part, divided by the whole, or the mass of the whole thing. So 161 divided by 269 times 100 will tell us that the anhydrous mass is 60% of the mass of the hydrate. Thus, the water part would be 40%. So for our final part of this podcast, let's look at some lab data and see how we would do our calculations for the glass bead on a wire lab. For example, if we were dehydrating calcium nitrate, that is a hydrate, how can we do the calculations? So the very first thing we need to do is find the molar mass of calcium nitrate or hydrate, and we can see that we would get 236 grams per mole, 164 grams from the anhydrous part, and 72 grams from the water portion, creating a molar mass of 236 grams per mole. That means that it's going to be 31% water part divided by whole, which will make it 69% anhydrous compound. All right, let's look at some lab data. If we heated that hydrated calcium nitrate until it decomposed and became a constant mass, showing that all the water molecules have evaporated off, we have a data set that's shown below. Take a second and process your data and calculate the mass of just the hydrate without the dish, the mass of the anhydrate, the anhydrous portion, and how much water was decomposed or evaporated in the process. For the mass of the hydrate without the dish, we should have gotten 7 grams. 57, the mass of the dish with the hydrate, minus 50, the mass of the evaporating dish, would tell us that we started with 7 grams of hydrate. We'll do the same thinking to figure out the mass of the anhydrate. We're going to take the mass of the dish with the anhydrous portion and subtract out the mass of the dish. So that would be 4.90 grams. And then the difference between our hydrated compound and anhydrous compound tells us how much water was decomposed or evaporated away. So 7 minus 4.90 gives us the water portion, which would have a mass of 2.10 grams. So now we can calculate the percent composition. And if we want to know the percent composition of water, the 2.10 will be our parts, and the hydrate mass will be our whole. So 2.10 divided by 7 times 100 tells us that we're 30% water. That means that we're going to be 70% anhydrous compound by mass. Again, 4.90, the mass of the anhydrous part, divided by 7, the mass of the whole, gives us 70% anhydrous as our answer. I hope this was helpful. Have a great day.